Hello, this is the walkthrough for the Year 9 chemistry test. This is on part 1 of the GCSE chemistry course on mixtures, particles, separation techniques and periodic table. So this is a test out of 44 marks. It was, on reflection, quite a challenging test in places with some easy bits. So I'm going to talk you through all the answers. But also I'm going to try and explain as much as I possibly can to you while you're doing that. When you're watching this video, you should have the test paper that you worked on during the test and be ready to make some corrections, to up level, make some additional notes, because that will help you to learn and to also do better perform better in other tests. So this is for AQA chemistry. As I said, it's all about particles and mixtures and atoms, and then onto periodic table. So question 1, students separating a mixture of 2 alcohols with 2 different boiling points. There's ethanol at 78 degrees Celsius and butanol that boils at 118 degrees Celsius. The first part is a labelling exercise, which most people do well. So A is a thermometer. Okay, and B is a condenser. Okay, or a Liebig condenser if you wish, but condenser is the key part there. And the last one is a round bottom flask. You can get away with saying flask. Really, we should try and say round bottomed. Try not to get confused with things like conical flasks, beakers and that sort of thing. They're quite different. The 2 things to really learn there. First of all, it's the separating mixtures part of the chapter. It is important to actually know each process in terms of crystallization, distillation, fractional distillation, and so on. So those are your 3 missing labels. The name of the separation process is distillation. It's actually fractional distillation. Excuse me. But distillation is absolutely fine here. Okay, because it's a 1 mark question, so if it's only worth 1 mark, then you want a simple answer. If this was 2 marks, you might want to think about saying a little bit more. So the point with fractional distillation is, of course, that you are separating 2 liquids, not a solute from a solvent. Sorry, a solvent from a solute. And that's the difference. And if visually, the clue is actually in here, in this part of the delivery tube, where you have this contraption here, which makes sure that liquids with higher boiling points recondense and go back into the flask. So suggest why the first liquid to be collected was ethanol. Well, if you look, the clear part here is that ethanol's got a lower boiling point than butanol. So that's basically your answer. Ethanol has a lower boiling point, or has the lowest boiling point. Okay, so that's basically it, relatively straightforward. And then the last part, part 1.4, question 1.4, it says alcohols are flammable, suggest how the mixture of alcohols could be safely heated. You can say all sorts of things, but the basic idea is keeping it away from a naked flame, but still heating it. So you could just use an electric heater. It would reduce the chance of a fire tremendously. Okay, so you could just use an electric heater. So on to question 2, and this was a question that was a lot easier than it looked. So question 2 shows a pair of gold rings. So there they are. Okay, it's giving you a pretty picture, very nice. But the important part shows the composition of gold, showing the metals actually used in that alloy. So you had gold, you had silver and copper. Okay, so all the question was asking, first of all, was stating the composition of the gold used to make the rings. So all we're really doing is you're reading the graph. So if you read the graph carefully, you draw your lines across. There we are, one there, and another one there. you then just have to read the scale. So each 10 squares going on the y-axis represents 20%. So every 5, 1, 2, 3, 4, 5, that would represent a 10%. Okay, 1, 2, 3, 4, 5. Okay, so you should recognize straight away this is 70, 72, 74. The next one's 76, but it goes past it, so this must be 75%. On silver, it's 10, 12, 14, 16%. And the copper is 2, 4, 6, 8, and there's another half, so that must be 9%. So the question just asks to state the composition of the alloy used to make the rings. Well, for gold, it's 75% gold. So we'd say 75% gold, 16% silver, and 9% copper. Okay, so if it's 9% copper, that adds up 9 plus 16 plus 75. That actually comes to 100%. So that's the composition of those gold rings. See, and that is a nice easy 3 marks. 2.2, an atom of gold can be represented as Au197. Au is the chemical symbol, 79 is the atomic number, 197 is the atomic mass of that atom. So it's got an atomic number of 79. Remember, that is the number of protons. It's also the number of electrons. 197 is the atomic mass, which means it's the number of protons plus the number of neutrons. So the atomic number, another word for atomic number is proton number. So there are 79 protons. As it's a neutral atom, there must be 79 electrons to balance it. Now, if the the mass number is 197 or 197, then to work out the number of neutrons, if 197 is the number of neutrons plus protons, you'd have to subtract the number of protons from that number in order to find out the number of neutrons. If you think about it, it's like having a bag with red apples and green apples. If you've got 197 apples and 79 of them are red, try and get that right. It's just my dyslexia creeping a little bit there. I'll just correct that. Okay, so in 79 of them are red, then whatever you subtract 79 from 197, and we end up with however many green apples there are. In this case, we do exactly the same, only the particles aren't apples, they're protons and neutrons. So it's 197 particles of protons and neutrons, 79 of them are protons leaving, subtracting, you end up with 118 neutrons left, okay? You do that, again, as I say, by subtracting the atomic number from the atomic mass. On to question 3. There wasn't a lot of space for this particular question, but we can still do it. You should think about how you would use salt and sand and to obtain salt crystals and dry sand. So the first thing we'd do is you would dissolve the salt in warm water. Warm water, it does help that it does help the salt to dissolve more easily. Okay, so dissolve the salt in warm water. Then we're going to filter the solution. So we're going to use a filter to filter the solution to trap the sand in the filter. Okay, so we're going to trap the sand in the filter. Then boil away the water in the salt water solution. Oh, gone off the bottom there. Here we are. Leaving salt. Then we're going to dry out the filter. And remove the sand when dry. Okay, and that's basically it. So you'd end up with your salt and you'd end up with your sand. And that's what it's asking you to do. It doesn't want the water. So it then says you should name all the apparatus you use. So you should talk about the apparatus. So part one is just basically making your solution with a mixture of sand in it. So you just take your beaker, your solution, okay, and you just show that you're using your beaker to do that, okay, with your sand in the middle, which you then filter. So you draw a diagram for a filter, for a funnel, first of all, and of course your beaker at the bottom to collect the stuff you filtered out, your solution. And you just draw on there your filter. There it is. Okay. So you've got your filter there. You've got your salt water and sand mixture, and you're dropping the solution into here. Okay. And then once you've done that, you then heat up the salt water solution with your Bunsen, and well, ideally you'd use a crucible, not a beaker, but basically what you end up with is just your sand in there. So you boil away the water, and you also take your filter paper and you end up with your sand on top. In an ideal world, what you would do is you'd list all the apparatus, okay? But I think this would take a very, very long time. But basically you're going to need a beaker, some water, a stirrer, a filter, a funnel, a filter. You're then going to need a Bunsen burner, tripod and gauze, a crucible, and possibly a heater if you want to dry out the sand more quickly. But that's basically what you're supposed to do. So the next question, question 4, it shows the melting points of group 1 metals. So we're well and truly into the periodic table now. So if you've got group 1 metals plotted against their atomic numbers, you get a graph with that sort of shape, and it says give 2 conclusions that can be drawn from the graph. So it wants 2 things. First of all, let's start off with the obvious. As the atomic number increases, then the melting point decreases. So that's a good place to start. As the atomic number increases, melting point decreases, or temperature at which it melts. But it wants a little bit more to get the second mark. So to get the second mark, you've got to say a little bit more about the shape of the graph. Well, if you have a very high atomic number, then actually that melting point doesn't change much, okay? So we could actually say, the change levels out. For large atomic masses. Okay, so that levels out for large atomic masses. There we go. So that's then worth 2 marks because you're saying 2 things. First one is the general trend. As the atomic number increases, the melting point decreases. And and then you're going to a little bit more detail. In fact, the examiner did accept the idea that if you said that as atomic number increases, the melting point decreases, and then said as atomic number decreases, the melting point would increase, they actually accepted that for the second mark. But this is a far better answer because the other example, I think, would be saying the same thing twice, more or less. So then we've got to get onto the stuff that we need to know. Okay, this is stuff you need to know, you need to be able to do. So the first one, 4.2, says estimate the melting point of francium. So all you're doing here is you're looking at francium. It's got an atomic number of 87. So all you're doing is you're using the graph. So we've got 80, 87 is here, okay? So you draw your line up to the graph line at 87, like that. And then you draw your line across from 87, like that, okay. Draw a line across carefully, and that should be, that's going up in twos because it's 20 for 10 for 10 small squares. So each small square is going to be 2, 2, 4, 6. So it's 26 is your actual temperature there. Okay. So once you've done that, you then just write it in there. Okay. The examiner would allow you to be about 1 degree out. So if you said 25 or 27, you get away with it. But if you started saying things like 24 or 22, that's the point at which the examiner decides that they're not going to give you the marks. And so the next part is to show the atomic structure of lithium, sorry, the electron structure of lithium. So what we're really doing here is we're taking our structure of lithium. Okay, so this is lithium. You've got your inner shell. We know that lithium has 3 electrons. So we know we're going to have 2 electrons on that inner shell because that's all that fits on the inner shell. And then the next shell, remember, if we've got 2 here, there are 3 in total, there's 1 left. So you just need to put 1 extra electron there. That was it, okay? So that's only worth 1 mark. So describe what you'd see when sodium is added to water. Now this is 3 marks, so they want at least 3 things. It's not enough to just say it will react. What do you mean by that? So we have to think about exactly what it does. Well, if it's sodium, remember sodium is not a very reactive alkali metal. It's if you put francium or potassium in water, it'd be far more reactive. So it doesn't necessarily catch fire, but what it does is, first of all, it fizzes, okay? It fizzes because it produces hydrogen, okay? Now it says say what you'd see. So you can't say it produces hydrogen because you can't see hydrogen. So you'd say it fizzes, okay? We'd probably notice that the sodium would float. It floats on the water. And we want a third thing. Well, it generates a bit of heat, so it melts. It's also good enough to say that it moves across the surface, also that it dissolves in the water. Okay, any 3 of those gets the 3 marks. Right, on to the next question, which is to do with the reaction of sodium with water. Now let's say, for the sake of argument, you had a complete panic. If you've got reacting sodium with water, all you've got to do is remember the symbols first of all. Well, sodium, it's on your periodic table. It's capital N, lowercase a. And for the water, it's H2O. Okay, you do need to know the chemical composition of water. Memorize it. Then that's worth 1 of the 2 marks straight away, even if you can't balance the equation. To balance it, we've got to make sure we have the same number of atoms before and after. So if we think about it carefully, we've got we've got 1, 2, 3 hydrogen being produced. Those are in our products. We've only got 2 hydrogen being produced in the in among the reactants. So we're missing a hydrogen atom. So we're going to have to double that because you can't get hydrogen from any other particle. So we double that one. So that then means you've got 2 times 2 is 4 hydrogen, And now we've got 1, 2, 3. So we need 4. So we need to double this one. We need to double this particle, this substance, in order to have 4 hydrogen, because we've got 2 times 1 is 2, add 2 is 4. So that's a hydrogen, now checks out. Now let's check out the oxygen. So we've got 2 times 1 is 2. 2 times 1 is 2. So the oxygen checks out. The last one is to do with the sodium. So the sodium, we've got 1 sodium atom at the beginning, and we've got 2 times 1 makes 2 sodium atoms afterwards. So that doesn't check out. We need another sodium atom because we've got 2 at the end, we've got 1 at the beginning, so we've got to double that one. And that's it, done. That's your balanced equation. So then the next part is to describe the trend of reactivity of group 1 metals with water, and you have to be quite precise in your language here. So it is, as you move down the periodic table, the reactivity will increase. Okay, so that is the description of the trend in reactivity. You can't say it will increase because we don't know if you're moving up or down the periodic table. You've got to be very careful about stating which direction you're moving in, okay? So once you're done 4.6, you then go on to 4.7. Now 4.7 looks identical to 4.6, but it is not, because 4.6 says describe. That means say what you'd see or hear or experience, what would happen. 4.7 says explain. That means you've got to say why. And it's worth 3 marks, so we've got to produce a really precise answer here. So there are 3 basic points to this. So the first part, okay, is as you move down the periodic table, as you increase the period or move down the table, this is how we've got to be very, very, very careful here. The number of shells, number of electron shells, but it's suffice to say that number of shells, because it's implied, increases. So the number of shells actually increases. In other words, which means that the outer electron is further away. Is further away from the nucleus. Which means it's less tightly bound. Which means, and so easier to remove. Okay, that's it. Once you've said it's easier to remove, that's it, job done. We've got 3 things that we said there. I think the most important part's here to say that the outer electron is further away from the nucleus, then it's less tightly bound to the nucleus, and so it's easier to remove. And that is enough to explain the reactivity of group 1 metals. So on to part number 5, question 5, almost there. So the table then gives some melting points of the elements in group 7. So now we're on to halogens. We notice we don't have the melting point of chlorine. I think that will come in later. So you want to plot a graph. It says plot a graph the melting point against atomic number. So we're looking at atomic number and melting point, and we've got negative numbers. Now they can be quite awkward to plot, so we just have to keep alert. So let's put on the atomic numbers. We've got 9, 35, 53, and 85. So in the atomic numbers, every 1 square is an atomic number of 1. So 9 is here, okay. 35 is here. 53 is 50, 51, 52, 53 is there, okay. And 85 for astatine is up here, 85, okay. Then we want the melting points. So for 9, the melting point is minus 220. So here's 200. Now again, every little square there represents 10 degrees. So minus 220, there's 210, 220. Okay, so where it's 9, it'll be 220. So you move up from the 9, move across from the 220, and you end up with your data point about here. The next one is bromine at 35, atomic number 35. Melting point is -7. So here's 10, so it's going to be slightly less than -10, so it'll be about there. As long as you're plotting within one square, you're absolutely fine. So the next one at 50, with an atomic number of 53, is 114. So that's 100, and again, 110 is going to be here, just a bit above it, about half a square above it. That's it, that'll do nicely. And then the last one, astatine, has an atomic mass of atomic number of 85 and a melting point of 301. So here's 85, here's 300. It's going to be as near as makes no difference 300, because it's much closer to 300 than 310. And then all you've got to do is plot your graph very, very carefully, as carefully as you like, something like that. Looking for a line of best fit, nice and straight. The job is a good one, okay? That's it. That's all they really want. You've got 1 point above the line, 1 point below the line. That's absolutely fine. So the next part says estimate the boiling point of chlorine. So, no, sorry, the melting point of chlorine. I do apologise. The melting point of chlorine. So chlorine has an atomic number of 17. So you've got 15, 16, 17. There's the atomic number of chlorine there. So take your ruler and draw your line up to the line of best fit. And then you draw it across like that. Well, it doesn't have to be perfect, but there we go. I make that minus 150, minus 160. Okay, so it's minus 160 degrees Celsius. Now, with this, you don't have to worry too much about exactly where the what the number is. What the examiner's looking for is the idea that you've read from the line. Okay. In fact, the value in the mark scheme is not actually anywhere near 100 minus 160, but this is fine. This works. Okay. This is absolutely good. Okay, so that then takes you as far as you need to go there. So the next thing to do is then go on to 5.3. So what is the state of iodine at 25 degrees Celsius? Well, if you've got iodine, its melting point is 114. So anything below 114 degrees Celsius, it won't have melted. It'll still be a solid. So 25 is below that, so it is obviously still a solid, okay? Chlorine has 2 isotopes. Why do they have different mass number? It is very simple, okay? It's the idea they have different numbers of neutrons. Okay? So once you've done that, you've actually established your number of neutrons that you've got. You realise you've established that you've actually got a different number of neutrons. Well, is that enough? No, it's 2 marks. So you're going to have to go just a little bit more, you have to go a little bit more in depth here. So what we're going to do is we're going to actually be precise. So chlorine 35, that's got, well, if we subtract 17 from 35, we end up with 18. So we know it's going to have 18 neutrons. Okay. And the chlorine 37, we subtract 17 from 37, that will have 20 neutrons. Okay, that's all I've done is I've just worked out the number of neutrons each time, and that was what was needed to get that second mark. You needed to really be very, very clear about what the difference is, and then an adequate comparison. So it then says a relative formula mass of chlorine is 35.5. Why is this not a whole number? It's because it is an average. It's an average value of atomic mass. Okay, that's the basic idea. The key thing the examiner wanted was the fact that it was the average over a whole sample of the chlorine. Okay, on to number 6. Now, this is all to do with the history of the periodic table. Yes, you do need to know it. So Dmitry Mendeleev was one of the first chemists to classify the elements. He created his periodic table. Which group is not in Mendeleev's table? You can either know it, or you can just or you can look for it. But if you compare it to the modern periodic table, you notice there's nothing from group 0 there. So group 0 is not in the periodic table. Mendeleev placed hydrogen at the top of group 1 in his version of the periodic table. The modern periodic table does not show hydrogen in group 1. State one similarity between hydrogen and the elements in group 1. So there are two possibilities here. The simplest is the fact that it's put in group 1 originally because it has 1 electron in the outer shell. Okay, that's the thing that they have in common. You could also say, because it was in group 1, it forms a +1 ion charge. Okay, so they're both capable of only losing an electron, not gaining them. On to 6.3, Mendeleev changed the position of iodine in his version of the periodic table. Okay, he put it in the same group as chlorine. Give 2 reasons why he'd do that. Well, the first one is it had similar properties. Okay, it's similar properties to other elements. In group 7, okay. You can also say lots of other things. You could also say that they form diatomic molecules. You could say that that it reacts with metals, just like all the other elements in period 7, in group 7. I think one of the easiest ones is also similar. It has a similar reactivity. In other words, it reacts in the same way as everything else in group 7. That's basically it. That's for 2 marks. Last but not least, you had protons and neutrons and electrons were discovered after Mendeleev proposed his version of the periodic table. Describe how the numbers of protons and electrons in atoms are used to place elements in the modern periodic table. So you're thinking about how it's ordered, and it's a 2-mark question, so it requires a little bit of work. So the next thing to think about here, well, first of all, remember it's not ordered by atomic mass, it's ordered by atomic number or proton number. Okay, so it's ordered by proton number. And also we'd say that each group has the same number of outer electrons. Okay, now it's enough for the 2nd mark. That's basically how you do it. So my advice would be make sure that you have gone through this paper, make sure you've done your corrections on your paper. In doing so, please do pause when you're playing this back so that you can write your notes more effectively and have time to do that. Do also skip over questions where you've got the question right anyway, and you certainly know exactly why. And make sure that you do know how to answer these questions. There's a fair overview of the work we've done so far this term, so it will also help you to remember some of the key ideas that we've covered. I'll leave you to it.